these types of problems on worksheet 2, what we're going to be doing is starting to look at what we can figure out, what we can learn from things that have a horizontal motion in addition to vertical motion. So our previous worksheet was just working with things that were thrown straight up or that were falling straight down. But now we're going to have the opportunity to look at things that are moving across a horizontal surface. So with this first problem, it gives us a situation where we've got a marble that's on a rail so that it has a nice little track to follow across the top of a table. If we have done something like this in real life, if you've ever rolled a ball off of a table, one thing that you'll notice is that when the ball leaves the table, it's going to move in an arc. So that ball is going to fall by traveling in an arc across space and land some distance from the table. It's not like the ball that, if it has any velocity at all, is going to reach the end of the table and then just fall straight down. That's not what actually happens. So first, it's a sketch and label force diagrams for the marble, both when it's on the rail and when it's off the rail. Describe horizontal and vertical motion of the ball in each case. So if we think about what happens when the ball is on the rail, this ball right here is not actually being pushed, even though it does have a velocity. It doesn't have acceleration horizontally. And it is experiencing downward force due to gravity and an upward normal force. The other thing that we know is that those two forces are balanced. So they should be equal in magnitude to each other. And that's why the ball doesn't accelerate upwards or downwards. However, as soon as the ball leaves the rail and is in the air, it no longer is experiencing normal force, and it is only experiencing gravity. And so if it's experiencing gravity without something to balance it, it's going to accelerate downward, because that's what this is indicating. If our force is equal to mass times acceleration, we're going to have acceleration in the downward direction that's coming from gravity. So up on the rail, we know that the magnitude of normal force is going to be equal to the magnitude of gravity, and forces are balanced. We also know that there is a constant horizontal velocity. Which means there's no horizontal acceleration, which is important. We know that off the rail, we only have force due to gravity. That's the only thing that's influencing the motion of this thing. So because there's only force due to gravity, we know that this is unbalanced and our object will accelerate downward. All right. Next part says, once the ball leaves the table, we need to calculate how long it takes for it to hit the floor. So this how long is asking us to solve for time. So what we need to do is figure out the things that we know so that we can use it to solve a problem. My recommendation is that with problems like these, you have a set of things that you keep track of that are vertical, and a set of variables that you keep track of that are horizontal. If you want to, you can just call them V and H. That's what I end up doing by the end of this unit for you guys. But for the purposes of these first problems, I go ahead and write the whole thing out. So things that we know vertically, this guy, this velocity here is a horizontal thing. You guys see how it's horizontal. So it's a horizontal thing. We know vertically that we're going to have a change in height of 1.5 meters, and that's our object going downward. So I'm going to actually say that we have a change in vertical displacement that is equal to minus 1.5 meters. So we know that. I also know that as soon as this ball leaves the table, its vertical velocity is 0. So over here, I'm going to say my initial velocity is 0 meters per second. And we've done that before when we have an object that's falling. We also know that our acceleration due to gravity is minus 10 meters per second squared. So there are three things there. So it asks us how long will it take for it to floor. With just those things, we can calculate time. We actually don't need to know anything about the horizontal motion to be able to calculate that time. But horizontally, we do know that our velocity is 10 meters per second. Okay, so in order to solve for time, what we're going to do is take a look at our cover page and see which of these help us. This whole column over here is horizontal motion. That's not something that we need to use right now. We don't have enough information to do it anyway. We do know velocity, but we don't know a distance. So we need to look over here. The information that we have is the displacement, initial velocity, and acceleration, and we're trying to find time. So the one that I would use is probably this quadratic one here. I know that it's the more complicated one, but that's where we are today. So our vertical displacement is equal to 1/2 times acceleration times time squared plus our initial velocity times time. We know that our initial velocity is 0, so we're not going to use that. Our change in displacement here, 1.5 meters, equals 1/2 times minus 10 meters per second squared times time squared, and we're going to solve for time squared. I think my daughter stole my calculator from my office. So I'm going to have to do this on my phone. Let's see. All right, so if we've got minus 1.5 meters is equal to minus 5 meters per second squared times time squared, then we know that time squared is equal to minus 1.5 meters divided by minus 5 meters per second squared. 1.5 divided by 5 is 3, I think. Oh, sorry, divided by 5 would be 0.3. Yeah. So this is going to be 0.3. Sorry, this is time squared. Second squared, so time is equal to the square root of 0.3 seconds squared, which is going to be... I'm not talented at doing this on my phone. I got 0.54 seconds. Now, the thing that's important about that is, remember, change in time is the thing that is the same, that bridges both of these. So if we solve for time in our vertical stuff, then we can use it over here in horizontal stuff. So if we know time, we can solve for how far away from the table our object is going to land. So part D says, in the time you've calculated in part C, how far will the ball travel horizontally before hitting the floor? So here, we know it's going to take the same amount of time to fall from the table to the floor as it takes for the ball to move from the edge of the table out to wherever it lands, because it's going to travel across this arc. This particular arc, yesterday we were talking about parabolas, we had time as our axis on the bottom. Here it's actually distance. It's actually it's a representation of how far that marble is going to move. So in order to solve for that, this is a horizontal problem because we want to know how far it travels horizontally before hitting the floor. So we're going to look over here to our horizontal motion equations, and we need to solve for our change in position along the x-axis. Sorry, let's get this. I've got a plant on my desk, and so it's in my way. All right, so we've got our change in x is equal to our velocity times time. So that position is going to be our velocity, which we knew. That's our 10 meters per second from the diagram, times 0.54 seconds. So it's going to travel 5.4 meters to the side. Next, it says, suppose the table was doubled in height to 3 meters. Determine the horizontal range of the marble as it falls to the floor. So here we're going to solve again for our change in x, not our change in y. This is why it's a little bit helpful to start paying attention to which variables we're using, because it's going to help us to be able to stay organized. What effect does doubling the height have on the range of the marble? What other factors affect the range of the sphere? So things that affect the range are going to be anything that's related to this equation. So we can affect the range of the sphere by changing either the table height or by changing the velocity. Those are the two things that will change it, because those are the things that come from the equation. The other thing we could change it, I suppose, is what the gravitational constant is, but the acceleration due to gravity, but that's not a realistic change to make. So sometimes people's gut reactions is to say, well, if you double the height, it's going to take twice as long for it to fall. The problem is that the height change. The time that it takes to fall varies with the amount of time that it takes based on acceleration. And since it is speeding up, that's not going to be a constant change. That's going to be something where it gets increasingly faster as it falls. And so it's not enough to just double it. It's actually going to take a little bit less than double the time to fall. So in order to do this, what we have to do is kind of go back to our information in part C and swap out this 1.5 for 3.0. So I'm going to kind of take this equation that we wrote up here, and I'm going to bring it down here. But instead, we're going to have 3 meters is equal to 1/2 times minus 10 meters per second squared times time squared. So we end up with minus 3 meters equals minus 5 meters per second squared times time squared. So time squared is equal to minus 3 meters divided by minus 5 meters per second squared. So double check, make sure I got this right. So we've got 3 divided by 5, which I think is going to be 0.6. Yeah, 0.6 seconds squared. And so time is equal to the square root of 0.6 seconds squared, which is 0.775 seconds. So that 0.775 seconds is not double the amount of time it took to fall before. And again, that's because in this first part, we're not falling as quickly as we are falling in the second part. It says determine the horizontal range. And so in order to do that, again, like we did for part D, we're going to do our change in position is equal to our velocity, our 10 meters per second, times our time, 0.775 seconds. So that's going to be 7.75 meters that it is able to move away. So if we double the height of our table, which I don't think I can quite do in the picture, but if I double the height of the table, I would actually have something that moved much farther away. Like maybe my diagram is not to scale, but it would move. It would have the opportunity to move farther away. And you can tell it's not going to move double, because to move double, we would have to really speed up the velocity to be able to get it there. All right, so it's 9:16 right now. What I would like for you guys to do in the time we have left is work on problems number 2 and 3 on the next page. They don't have as many steps, so hopefully that should be a little bit simpler for you. What I'm going to do is stay in the Google Meet. I would like for you guys to work on these questions. I am not going to require that you guys stay on camera, and I'm not going to require that you stay in the Meet, but you do need to have these done before class time tomorrow so we can go over them. All right, does anybody have any questions for me?